Good morning, everybody. My name is Ashutosh Garg. I work as solution provider with Furnace Improvements. We are in the business of improving run length of crude heaters, vacuum heaters, and improving their performance. We completed 25 years this year. So as a part of our Silver Jubilee celebrations, we have been conducting free webinars for all our customers this year. Welcome today to our webinar on crude heaters. We have almost 85 registrations, so I'm really thankful for the response we have received today. Thank you for your time and thank you for your interest. We will have the session for about 45 minutes, and a number of you have submitted many questions for the webinar. So we will try to answer as many as possible today. If not, we will take them in the next webinar, and we may even have a QA session on crude heaters. It's such an important topic. So without any further delay, I will start our webinar, and I'll start with a brief introduction. I think most of you know me. I'm a chemical engineer from IIT Kanpur. I passed out in 1974. And since 1976, I have been working on fired heaters and combustion systems. For the past 25 years, I've been working with furnace improvements on fired heaters, burners, low NOx systems. That's what I've been doing for 25 years. So let's move on. So today we'll be talking on crude heaters. Crude heaters, as you all know, are one of the largest heater in the refinery. They are the most important heater. It is the first heater which the crude comes in contact with. Crude heaters are low pressure heaters compared to others and have two-phase flow. One of the issues with the crude heaters, and for that matter, all the refinery heaters, is run length. And I want to talk to you about my own experience. Back in 1977, I was working in India, and we got a chance to work on two crude heaters at Indian Oil Refinery in Gujarat. These were Russian heaters. They have already been replaced, but they were Russian heaters and they were consuming a lot of atomizing steam. In fact, the atomizing steam was almost like 1.1 kg per kg of oil. And IOC wanted to reduce the steam consumption, so they hired the company to replace the burners. And I was at the site for almost 2 weeks and talked to a lot of operators and engineers. And at that time, the run length was typically around 1.5 to 2 years for crude heaters. That was the norm at that time. Now fast forward 30 years, 2008, we are contacted by Citgo in Lake Charles, US. And they tell us, hey, we need to design a crude heater and vacuum heater, and we are looking for 8 years run length. Now 8 years is a very, very long time. We accepted the challenge and we designed the heaters, and today I can say with pride that those heaters did achieve 8 years run length. I will show you how we did it. But the norms have changed. In US, prior to 1980, we used to have 300 refineries. Today, we have only 120 refineries. So we are in the survival mode, and the fittest refineries will only survive. All small refineries, all unprofitable refineries have shut down. So today, the utilization factor in US is close to about 92 to 93%. So that means you had to run your heaters all the time at full capacity. We have not built a new refinery in US since 1980. Now that situation is very much in contrast with the situation in India, where we are still building a lot of refineries. So it's a very different situation, but the objectives are basically the same. So we'll talk about crude heaters, and then we will talk about the important design parameters. What are the important parameters which affect the coking, which affect the run length? And we have developed a very simple coking index, which can determine whether the heater will coke faster or later. And we will present some case studies where we worked with the clients and improved their run length. So that's what we will do in the next 40 minutes. So all this would not be possible without the support of furnace improvements team. My team has been working very hard for the past 4 weeks in developing the webinars. So I have to do a little bit of infomercial so that they can pay the bills. Furnace improvements was started in 1996 by me. And I can tell you a story actually. In 1994, I was in Texas City, and there we saw a number of refineries. Actually, if you have been to Texas City, there are almost 4 refineries right next to each other. So you could see almost 100 heaters. And I asked my colleague, who was a sales manager, Bob, and I asked him, hey, who is looking after these heaters? And he said, nobody. I said, why? He said, fixing heaters is a dirty business. It's a troubleshooting business. You don't get any credit. So most of the heater vendors have been focusing on new heaters. Everybody likes having new heaters, so that's what most of the heater vendors work on. However, in 1996, when I got an opportunity to take my career in a different direction, I decided to take on this challenge. And I said, hey, let me work with the end users and owners directly and fix their heaters. So 90% of our business is fixing heaters. Old heaters, we improve their capacity, we improve their run length, we improve their efficiency, uh, increase their capacity. So that's what we have been doing. 2005, we opened an office in Noida in India. 2014, we opened an office for doing CFD in India. And there are two things I want to talk about, what differentiates us from other companies. One is the name improvements. We are always looking for improvements. Just like in the computer industry, you will see if you want to change your hard disk, you will always try to upgrade it to SSD or to higher capacity. It's the same thing. If you come to us for changing the convection section, we will upgrade it. We will let you know that these are the options available. And the second thing is we have a contrarian approach. We always challenge the conventional wisdom. We will try to do the root cause analysis and try to come up with new solutions. and we have been very successful. Today we have 4 patents, and we will tell you today about one of our technologies. So with that out of the way, let's go back to our crude heater. Any refinery you will have anywhere between 15 to 60 heaters. And you all know heaters are high temperature equipment. Most of the heaters in the refinery are processing hydrocarbons, and hydrocarbons are prone to cracking, and thereby we have coke deposits and we have run length issues. But let's start with the crude heater. Crude heater is the first heater, one of the most important heaters. It is the largest heater in the refinery, where crude comes in contact with. It is preheated, and then the crude is sent to the atmospheric distillation tower. The bottoms of atmospheric distillation is sent to the vacuum distillation towers, and then all the residues from the vacuum and all the other units are sent to the coker heater, where the products are converted into coke and other profitable products. And then we have reformer heater, which is meant for improving the octane number of gasoline. So these 4 heaters, in our opinion, form the major backbone of any refinery. Very, very important heaters, and today we are focusing on crude heater. I want to give you must be more familiar with this process flow sheet, where the crude comes out, it goes to a desalter, then it is preheated in exchangers, and then goes to a crude heater, where it is heated to almost like 700, 725 degree F, and then it is sent to the atmospheric fractionation, where we take out different products. So this is what we is in nutshell crude heaters. I want to thank you for sending us tons of questions. Our team has listed about 10 or 12 questions over here. Thank you again for sending your questions, and if you have more questions, please send it through the webinar question box. We will try to answer them today. If not, we will put them on our Facebook and LinkedIn page. These are very relevant. We want to cover the topics which are of interest to you, and the pertinent questions relating to the coking, relating to the run length have been listed over here. And we will try to cover most of these today in our presentation. Here is another slide for attendee questions for how to minimize the fouling, how the burner performance change with the change in fuel. So we will try to see what all we can answer today. So crude heaters, we have been working on crude heaters for almost last 25 years. In fact, our first job was on a Citco crude heater. That was our first job. Here, what we have listed is the typical design parameters for crude heaters. The inlet temperature, depending on the crude preheat, can range from anywhere between 400 to 600 degree F. Outlet temperature around 625 to 725. Outlet pressure, as I said, is very low, 25 psig, because we have atmospheric distillation going on. The pressure drop across the heater could be anywhere between 100 to 200 psi, although we have seen some crude heaters with as little pressure drop as 50 psi. Typical coil material in the radiant section is 5 chrome half moly. That is a very typical this thing. And average radiant heat flux which has been used is anywhere between 10,000 to 12,000 BTUs per hour foot square. Fluid mass velocity between 250 to 350 pounds per second plus foot square. So we have worked on almost, like I would say, 30 to 40 crude heaters in the last 25 years. And we had a database. I just want to talk to you. We had a client who was getting 3 months run length on in their heater. They changed from Arabian crude to shale crude, and their run length dropped from 5 years to 3 months. I will show you how we help them. We had a client who was getting 1 year run length in their heater. In fact, the situation was so bad that they had wrapped their tubes in ceramic fiber. We had a client who had 2 tube failures in 3 years. And imagine whenever there is a tube failure, there's an immense loss of productivity and a big cost to fix the heater and a large shutdown. We had a client who was draft limited in their crude heater, and we fixed those problems. So I will show you some of these cases today, maybe in brief, but I will talk to you about how we have worked with our clients in improving their run length and improving their performance. Before we move on, I want to talk about typical crude heaters configurations. I think you are all familiar. Vertical cylindrical configuration is one of the most popular configuration for fired heaters, including crude heaters. It has a lot of advantages. The biggest advantage is the cost. It requires also low plot space. You have vertical tube, and generally about 40-45 million kilocalories you can easily accommodate in a large vertical cylindrical heater. Box heaters have been, like I should say, the evergreen heaters, horizontal tube heaters. Actually, the industry, when it started with horizontal tubes, and horizontal tube heaters have been there. They are a little bit more expensive, about 15 to 30% more expensive than vertical cylindrical heaters. And they also require large plot space, especially for tube removal. So that said, they are still very popular. They are still very popular. And then the last one, what we have seen is this high intensity multicellular heater. These heaters came into being in 1960s when there was a trend to use very high capacity burners. Now we find that these heaters are not having very good performance because of low NOx burners. We have to shift to low NOx in almost all the cases. Also, in terms of operation, I would any day prefer a horizontal tube box heater or even a vertical cylindrical heater than a high intensity multicellular heater. You can put these heaters if you are tight on space. So this is a very, very compact heater, and there are several heaters in US with heat duty of 250 to 550 million BTUs an hour. So those are the three major configurations which are used in fired heaters. Now let's move on to the main issue and that is the high tube metal temperatures. That is the reason we have to shut down the heaters, the run length gets limited, and we have to clean it. So most of the experiences, most of the high tube metal temperatures are caused by flame impingement. It could also be as a result of overfiring. We have seen a lot of heaters where the heat exchanger train does not provide the required inlet temperature, and the crude heater has to bear the brunt of that temperature loss. So as a result, the operators still try to get the same coil outlet temperature, and it kind of leads to overfiring. So there is basically two things which add to the high tube metal temperature, and we normally have coke inside, which can give high temperature rise, and we can also have scales, and these can lead to high tube metal temperatures. Now, in a good heater, the thumb rule is your tube metal temperature should not be more than 100 degrees above your fluid outlet temperature. So if your fluid is at 700, your tube metal temperature should be about 800 degrees. That's generally the industry thumb rule. If you're seeing 900, 1000, 1100, I can assure you, you either have scales or you have coke, or you may have bad thermocouples. We should not rule out the possibility of bad thermocouples also, but that's what you would try to see all the time. So let's see what happens. Coke, which is formed by cracking of hydrocarbons, can deposit either as a hard dense coke, and in that case the thermal conductivity is 30, or it could be a light fluffy coke, and then in that case the thermal conductivity is much lower. In any case, if you compare the thermal conductivity of the coke with the thermal conductivity of the metal, whether it is carbon steel or stainless steel, you will easily see a ratio of 1:10 or 1:20. And the thumb rule is 1/8 of an inch of a coke will give you 100 degrees increase in the tube metal temperature. That's basically the industry thumb rule. So if your tube metal temperature is about 900, 950 degrees, your outlet is 700. Typically, it could be 1/4 of an inch of a coke, or maybe even little more than that. That's generally. Now, anytime you have coke, you will get high tube metal temperature, your pressure drop will start going up, your firebox temperature goes up, firing rate will go up, your thermal efficiency will go down, and you will be limiting in the charge rate, and ultimately you will have to shut down the heater and clean the tubes. That's typically how the coking works in most of the heaters. So what we want to do is to avoid coking, minimize coking, so that we can extend the run length of our fired heater. Let us see how the heat transfer takes place in fired heaters. In the fired heaters, there are two major radiation modes of heat transfer. There is a direct mode which comes from the hot flue gases and flames. And there is an indirect mode, which is basically the re-radiation from the refractory walls. And you will see that that is the difference between boilers and heaters. And then we have a small component, about 15%, which comes from the convection by the movement of hot gases. So these are the three modes of heat transfer which start from the flue gas, goes to the metal, tube outside. And then we have conduction taking place through the tube wall. And here there can be two valence. There can be scale on the outside or coke on the inside. And we want to minimize both of them to get proper heat transfer from the outside of the tube to the inside of the tube. And finally, the convection into the process. Finally, that heat has to be transferred to the process fluid. So we want to have good convection coefficient inside. We want to have high velocity so that the heat can be taken out. So that has been the heat transfer mechanism in the radiant sections. One thing I want to tell you is that radiation is independent of the distance. And that is a good thing. You can keep your flames away from the tubes. Your flames does not need to be near the tubes, and that will improve the run length of your heater. So fired heater are almost about 120 or 130 years old. And the old design of fired heaters did not even have a radiant section actually. They were all based on convective heat transfer. It was in 1939, the two brilliant engineers, Lobo and Evans, they came out with their correlation and said this is how the radiant heat can be transferred in the radiant section. Now, they made some assumptions, and one of the major assumptions was that firebox has a uniform flue gas temperature, and the heat transfer model is continuously CSTR, continuously stirred tank reactor model. So with these assumptions, they had done the correlations. And maybe at that time, these were working well because the shape of the radiant section and the burners was very different. The heaters were very short, and there were lots and lots of burners. So maybe the CSTR model worked at that time. But today, when we look at the heaters, we get a totally different picture. And I want to show you something. This is an actual VC heater, and we have done the heat flux profile. And you can see the heat flux in the top 1/3 is 7,000, middle 1/3 is 15,000, and the bottom 1/3 is 22,000. So whereas the average is 13,500, So you can see there is a big difference today, and that is why we have to be more careful in estimating the run length and maximizing the run length. I have not seen a heater today with a uniform heat transfer or model. So let us talk about the parameters which determine the run length of the furnace. On the coil side, there are three parameters. We have fluid mass velocity, average radiant heat transfer rate, and pressure drop. I think I have covered these parameters in my previous webinars, so I won't go into too much detail, except telling you go for highest fluid mass velocity and lowest radiant heat transfer rate if you really want to have good run length in your furnace. And if you're designing a new heater, take these two parameters, fluid mass velocity and heat transfer rate. Now, once it comes down to fire side, and I want to tell you that it is the flue gas side which is controlling all the heat transfer in fired heaters. We are looking at heat release per burner, burner to tube clearance, burner to burner spacing, and burner air side pressure drop. These are the four parameters which we have identified can help you get better run length in your crude heaters. And we have proof actually, so we will show you. So the first one is heat release per burner. Our recommendation is to use as many burners as possible. Small burners, small flames, will lead to uniform heat transfer. So that's what our recommendation would be, to go for small burners. Although the industry is going in the reverse direction, industry is putting larger burners, and that's why they are having a lot more problems. I don't know whether you are aware, API had to establish a special task force about 7 or 8 years ago, because heaters were having a lots and lots of problems when they were using the API 560 correlations for burner to tube distance. Burner to tube clearance, very critical dimension, and our recommendation is burner flames should be away from the tubes as much as possible. So try to go with higher clearance. That's what we will suggest to you, and it is possible. Another thing what we have found is burner to burner spacing. We think burner should be, if you want good run length, put lot of burners close to each other so that you will get smaller burners, uniform heat release, and uniform heat transfer. So again, very important. And then we have the air side pressure drop. You already maximize the fuel gas pressure around 15 to 25 psig. We think increasing the draft loss on the air side can also help in getting you better flames. And our recommendation is use forced draft burners wherever possible to improve the heater reliability and operation. So I have listed the 7 parameters over here. There may be some more, but basically, as I said, you can look at some of these parameters: average radiant heat flux, burner heat release, burner to tube spacing, burner to burner spacing, and burner air side pressure drop. And correct use of these parameters will help you achieve the lowest possible coking index. So one thing which we want to show to you today is our inclined firing technology. As you know, high tube metal temperatures is the biggest problem in fired heaters. And most of those things happen because the flame lengths are very long and we get localized flame impingement. So we have developed this technology where we incline the burners away from the tubes. And by doing that, we are able to move the flame and hot flue gases. And this does not affect your heat transfer. As I said, the radiation heat transfer does not depend on distance. So what we have been finding is just by inclining the flames, we are able to get anywhere between 100 to 200 degrees lower tube metal temperatures in most of the heaters. Very simple modification, simple concept, and it is very much relevant in vertical cylindrical heaters and heaters where you have low NOx burners. Low NOx burners, what you should understand is that NOx reduction comes at an expense of flame quality. Any NOx reduction means longer flames, lazy flames. That's basically the bottom line principle for achieving lower NOx. Burner vendors don't tell you, but that's what I'm telling you. And especially in existing heaters, if you have low NOx burners, you will have long flames and you will have nothing but problems. So by inclining the burners, for every 10-foot height, we gain extra 1 foot away from the tubes. And we have installed it in several heaters and have been very successful in improving the run length and performance of the heaters. I want to show you this case. This is from Valero in Texas City Refinery, a heater which was having number of issues. I mean that tube metal temperatures were close to about 1200 degrees. They were even exceeding the design values. Had already 3 shutdowns. September 2010, July 2011, that means only 9 months run, and then about January 2014. And they were not even able to get the outlet temperature. They wanted 700 degrees. They were only operating at about 640, 650 degrees. So they came to us, we studied the heater, we looked at several things we could have improved, but all we did, which was the most cost effective, was to incline the burners. In this case, we ended up using new burners, and we inclined the burners at about 7 degrees. We got improved flame patterns. And all I can tell you is the flame length, did increase a little bit, but the run length has been more than 5 years. The heater has been running since 2015 or 2016, I would say, and has been working fine. There has not been any issues. So very, very simple concept. And you can see over here, this was the heater before, and you could see the straight flame impingement taking place over here. And afterwards, the flames are in the center, and all this is cold area over here. So it does make a big difference. And you can see over here, we are comparing the coking index, and you can see we are lower than by almost 3 times, even though this is the actual run length increased by almost 5 times, but we still, theoretically, we are seeing 3 times the benefit. And we only changed the burners, that's all we did. This is another heater, and there was a question about crude. Actually, in this heater, the client changed from Arabian crude to shale crude, and his run length came down from 5 years to 3 months. In fact, the situation was so bad that they started injecting antifoulant, and that antifoulant was costing them millions of dollars every month. That is how much. So they came to us, we said, oh, we just want to double the run length. That's what their expectation was, because they were decoking it every 3 months. So they said even doubling will be fine. We looked at the heater, we came up with the new burner layout. And by putting new burners, we were able to increase the heater run length by 8 times. That means from 3 months, we went to 2 years. Just by burner change out. The client has been extremely happy. You can see over here the CFD model of the existing versus the proposed or revamped. And you can see even our coking index calculation is showing 3 times benefit. It is still not showing 8 times, but it is showing 3 times benefit. So it is a conservative calculation, but we do get benefit over here. This is another case where we had a heater at Phillips in Wood River Refinery. This was a very large heater, 200 million BTUs or 50 million kilocalorie twin cell, and they were charge rate limited, draft limited. Their stack temperature was very high. And we said, okay, we will put a new convection section and new stack. And by doing those two things, we were able to improve their efficiency by 7% and also improve their capacity by 25%. And here is one thing which I want to tell you is do not overlook convection section. Convection section can be your best friend. You cannot upgrade the radiant section, but you can always upgrade the convection section. See over here in this slide, you see the existing convection section and you see the proposed or the revamped convection section. Our revamped convection section was 4 times bigger than the existing convection section. But once we put this new convection section, the client was extremely happy, and he says, I don't know what you did, but you did magic. I mean, they have so much heater now with no issues that they are extremely, extremely relaxed. Their fuel gas consumption has come down. and their run length has gone tremendously up. Their capacity has gone tremendously up. So you can see we were able to increase the heater capacity from 215 to 278. We were able to improve the efficiency by 7%, reduce the stack temperature, So very, very successful project. So do not overlook the convection sections. And this next one project, which this is a project from HPCL Vizag. I did about, I think, maybe a little more than 10 years ago, 2009, I happened to meet the director technical of HPCL in Houston at one of the exhibitions. And he said, why don't you come to Vizag and look at our crude heater? And I said, sure. I came to Vizag. They were already in the process of revamping or replacing the convection section by an identical convection section. And I said, that won't solve your problem. And I gave them a solution. I said, you are putting a new convection section. Why don't you take the existing convection section and put it on top of the new convection section? So basically, they had this convection section which they were fabricating, and then we put the existing convection section. I think they retubed it also because they had the tubes. But this is, we went from this convection section size to this convection section size. So convection section is very, very good friend if you want to increase the capacity, if you want to improve the run length. We can shift the high flux from radiant to convection. And you can see over here, we increase the heater capacity by 15%, efficiency by about 5%, and we also reduce NOx. In fact, this heater had 12 burners and 4 burners were in the center, 8 were in the outside, and they were having a lot of issues with respect to the air distribution. We said, why don't we go from 12 burners to 20 burners? And we were able to put those 20 burners, recommend them 20 burners, and came up. And you can see, even though coking was not the objective here, but we reduced the coking index by almost 4 times. So we have a very wholesome approach. We try to do the root cause analysis and try to give you the best possible heater anytime we work on your heater. And this is what I want to end up with. This is the heater which we designed for 8 years run length. And we did not do anything big. We used the lowest flux, 10,000. We used a higher fluid mass velocity. We used a lower coil size, smaller burners, have a high burner to tube clearance, higher burner to air side pressure drop. And by doing this, we were able to get, as compared to the 70, we were able to reduce the coking index by 5 times. So 1/5, coking. So we were able to really achieve 8 years run length in this heater. And we did this not only in the crude, but even in the vacuum heater. So it is possible to get 8 years run length if you do the right steps, if you take the right steps. So here is a list of all the crude heater revamp projects we have done. And in the end, I want to thank you for the webinar today. Your questions and comments are welcome. We look forward to talking to you again soon. Thank you and have a nice day. Bye. Any questions? If you have, I don't see any questions here, but we will definitely. So thank you all. Bye.